bucka. Ha. You know the deal.
The next thing we're going to talk about in our unit on ratios is what's called similar triangles. So here on the board you can see I've drawn two triangles, and in each of those triangles we have the same angles. We know angles inside of a triangle have to add up to 180 degrees, and they do here. So here with the smaller triangle, you can see in the bottom left corner we've got a 90-degree angle. In the bottom right corner we have a 30-degree angle, and our top angle there is 60 degrees. Now the second triangle is bigger, but the angles are the same. And it is possible to draw two triangles that are different size but that have the same shape. And when we say that they have the same shape, we're usually referring to the angles here. So these two triangles do have the same shape because the angles are the same. Well, there is a relationship between the lengths of the sides. As we can see from these two triangles, the lengths of the sides are definitely not the same. The second triangle is bigger than the first triangle. But there is a relationship between the lengths of the sides. So, for example, if on our smaller triangle, that side was 5 units long, this side was 12 units long, and say this side is now 13 units long. Well, on our second triangle, if this side is 10 units long, what that means is the side on the bottom here has to be 24 units long, and the side that connects the 60-degree angle and the 30-degree angle there has to be 26 units long. And if we look at any two corresponding sides here, let's say we take this side, which is 5 units long, between the 60 and the 90-degree angles. The corresponding side there would be this side, which is 10 units long, because it's also between the 60 and 90-degree angles. Well, if we look at this in terms of a ratio, the ratio there is 5 units to 10 units. For, say, between the 90-degree and the 30-degree angle, here we have 12 units long, and the corresponding side there, between 90 and 30, is 24 units long. So there the ratio is 12 to 24. And finally, on what's called our hypotenuse, across from the 90-degree angle, between the 60-degree and the 30 degrees, we have 13 units on our smaller one, and 26 units on our bigger one. So our ratio there is 13 to 26. Now, with each of these ratios, if I reduce this to simplest form, well, for the first one, both of those can be divided by 5. That's the biggest value that goes into both of those. For the second one, both of them can be divided by 12. And for the last one, both of them can be divided by 13. So when we reduce them to simplest form, we see that we get the same ratio. And this is essentially the relationship between similar triangles, between the lengths of the sides of similar triangles. With the angles, similar triangles will always have the same angles, but the corresponding sides, the lengths are not the same, but there is a ratio that is the same. It's not necessarily always 1 to 2, but there is a ratio that is always the same between the corresponding sides. So let's look at another example here, and here we have two triangles, one smaller and one bigger. And we're given two of the lengths of the sides on the first triangle, but only one of the lengths of the sides on the bigger triangle. Now, first thing we have to do here is determine whether or not these are similar triangles. If they're similar triangles, the three angles will be the same. And here you can see I've only given two of the angles. One of the angles is 30 degrees, and the other angle is 40 degrees. Well, as we discussed earlier in the year, we know angles inside of a triangle have to add up to 180 degrees. So that means this angle here has to be 110 degrees. So with the bigger triangle, this angle here also has to be 110 degrees for the same reason. 30 plus 40 plus 110 makes 180. So we've confirmed the fact that these are similar triangles. So the next thing we have to try to determine is, well, what is the ratio between the lengths of the sides? And we're given two corresponding sides. Between the 30-degree angle and the 110-degree angle, this side is 3 centimeters. And on the bigger one, between the 30-degree angle and the 110-degree angle, that side is 9 centimeters. So our ratio here is 3 to 9. If we reduce that to simplest form, it's 1 to 3. So with our unknown side here, well, if we look at our given side of our smaller triangle is 10, and we don't know the corresponding side here between the 30 and the 40-degree angle. So if we look at this in terms of equivalent ratios, well, my first number here refers to the smaller triangle, so that's my 10, and it's 10 to something. That something is the question mark, what we don't know. Well, with equivalent ratios, we change 1 to 10 by multiplying it by 10. So we have to do the same thing to 3. Multiply it by 10. So what we find is that unknown side there is 30 centimeters long. Because these are similar triangles, they have the same shape but not the same size, there is a ratio between the lengths of the corresponding sides, and here that ratio is 1 to 3, which we figured out by looking at these two given corresponding sides. So here's another example where we're asked to find an unknown side of a triangle. And hopefully we're going to be able to use similar triangles here. So the first thing we have to look at is, are these similar triangles? And if they are similar triangles, that means they have the same shape, which means they have the same angles. And we can see here that they do have the same angles. Each of them has a 90, a 40, and a 50-degree angle. So we're given a couple of corresponding sides. Here I've kind of turned the second one, so it's not quite so obvious what the corresponding sides are. But if I look at my 8 centimeters here, that's between the 40-degree and the 90-degree angles. So my corresponding side there is my 12 centimeters. So my ratio here is 8 to 12. Well, if I reduce that to simplest form, that reduces to, I can divide both of those by 4, so we get 2 to 3. Now, what we're looking for here is this unknown side, which is between the 50-degree angle and the 90-degree angle, which I've given here on the bigger one. So on the bigger one, it's 10 centimeters. So if we look at our ratio here, we know the second number goes with the bigger triangle. So that's our 10 centimeters, and it's something to 10. Now, here's where we run into a little bit of difficulty, because it's not so obvious to see how we change 3 to 10. Well, we have to multiply it by something. So if we use our calculator to see, well, what do we multiply 3 by to make it 10, we have to do 10 divided by 3. And 10 divided by 3 is 3 1/3, or 3.33333, and so on. So we have to multiply 2 times 3.333, because that's what we multiplied 3 by. And when we multiply 2 times that, we get 6.6 repeating. So the length of that unknown side there is 6.6 with a repeating decimal. So to finish off our lesson on properties of similar triangles, I want you to answer a couple of questions here. For each of these triangles, I want you to use the properties of similar triangles to find the unknown side, so the side with the question mark next to it. So first determine whether or not they are similar triangles. Figure out what the ratio is between the lengths of the side, given the corresponding sides, and then use that ratio to calculate the length of each unknown side. If you're able to do that, congratulations, you now have a firm understanding of the properties of similar triangles.